Let's look at the path taken by a projectile. The problem is, a point-sized object is hurled at velocity v, making an angle theta with the x-axis. Compute the range and the maximum height of the projectile. Assume no air resistance and consider g, the acceleration due to gravity, as constant. So in this figure, the point-sized object is hurled at velocity v, making an angle theta. So that trajectory marked as 1 is the path taken by the projectile. Likewise, when the angle of projection is changed to a different one, but hurled at velocity v, then the trajectory marked 2 is the projectile's path. Likewise, as the angle theta changes, the paths change as depicted here. Paths 3 and 4 correspond to different angles at which the projectile is thrown. Path 4 is a highly ballistic trajectory, whereas path 1 is a less ballistic trajectory. So the notation is v is the velocity of hurl, theta is the angle of hurl, h max is the maximum height for a given v and theta, and r is the range of the projectile. So now the v is the velocity of the hurl and theta is the angle of the hurl. So the v may be now decomposed into horizontal and vertical components. You have v cos theta is the horizontal component along the x-axis. The axes are shown here. This is the x-axis and this axis is the y-axis. Likewise, the v's y component is v sine theta. So the horizontal distance is given by x equal to v cos theta times t from x equal to ut. Likewise, the y distance is given by v sine theta t minus half gt squared. Now these two equations marked 1 and 2 are the parametric equations of the trajectory, of this trajectory. And the parameter is time in this case. Upon eliminating t, which we could in this case, for these two parametric equations, t could be eliminated. And the way we do that is just solve for t from equation 1 as t equal to x by v cos theta and put the value of t in equation 2. And we'll be getting the equation of the trajectory as y equals x tan theta minus gx squared upon 2v squared cos squared theta, which is marked as equation 3. This equation is an equation of a downward parabola because, first of all, it's a parabola because it is quadratic in x. The highest power of x is 2. And the coefficient of x squared is negative. It's negative g by 2v squared cos squared theta. Okay, because the coefficient of x squared is negative, strictly negative, it must be a downward parabola. And so it is, as we see from these pictures. It's a downward parabola. Now, to get the range, we need to look at the x-intercept of this trajectory. So the range is basically the x-intercept, that is the points where the trajectory is cutting the x-axis. The chord is actually the range of the projectile. So we can get the chord by equating equation 3 to 0, the range equation to 0, one of whose solutions is x equal to 0, which is a trivial solution. The non-trivial solution is the range of the projectile as marked here, the length of the chord. It works out to be v squared sine 2 theta by g. So this is the range of the projectile. Now to get the maximum height, this is the maximum height. The maximum height occurs at half the range, as we can see from the symmetry of the diagram. So which is what we actually observe when we make the calculation with the equation of the projectile. This is the equation of the projectile, and the max height occurs where dy by dx is 0. So we differentiate equation 3 with respect to x and solve for x, giving the value of x for which y is maximum or the height is maximum. And that x, where max of y occurs, is half of this range, which is v squared sine 2 theta by 2g, half of equation 4. To get the h max, the height. So we need to substitute x max into the equation of the parabola, the equation of the projectile. Okay, so we put x equal to x max, and we get h max as v squared sine squared theta by 2g.